Hi, natural science friends. It's Mr. Frida. I just wanted to record another video for those of you who may have missed class on Friday or Monday at the end of January here. This is the review that we had prior to the Newton's laws, momentum, and impulse test. If you still need to take that test, I'm hoping that you're going to watch this video all the way through and think about the review questions before you come in to take the test so that you can be a little bit better prepared to understand what sort of learning and understanding you're going to be required to show me when you actually come to take the test. So we started off the class that you missed either Friday or Monday, looking at this data. And what I'd like you to do now is just look at the data, get a sense of it, maybe pause the video and decide what can we walk away by looking at these data. Okay, did you do it? So we obviously have an increasing trend in deaths here, especially in 1970 and 1980. And this might lead us to think that, oh my gosh, cars are getting unsafe as time goes along. What's happening here? And we ask the next big question is, what might we be missing from these data that we would need to know in order to make a judgment about the safety of cars? Pause the video again and think of some things that you can think of that would be nice information to have before we made a judgment call. Okay, hopefully you got some. So if I give you more information, what does the new picture look like? Well, there are a lot of things that could influence car deaths beyond just how many deaths there are in a year. And so if we look at this new set of data, we see that we have year-end deaths are identical to the prior information. And then we also have added population. You can see that the US population more than doubled from 1920 to 1980. We have 100 million more people, so that means more cars on the road. And when you actually look at deaths per 100 million miles traveled, you can see that that number has been falling consistently from 1920 to 1980. And so with more information, we see a very different picture of the data. We're getting fewer deaths per 100 million miles traveled. In other words, as we add more cars to the road and have more people driving, we're getting fewer and fewer deaths as car safety features are kicking in. Now, what happened in the 1970s and 1980s? Seatbelts became more common. We had the introduction of airbags in the late 80s and early 90s. In fact, the most recent statistics that we have for 2012 shows that deaths per 100 million miles traveled is down to 1.12 deaths per 100 million miles traveled. So the safety features in cars are making a difference. And what are those safety features? Well, those safety features are related to this concept of impulse that we talked about last week. Impulse is a change in momentum. In a car collision, momentum is always going to be transferred. 100% of that momentum gets transferred to something. A huge chunk of it gets transferred to the other object. Some of it might get transferred to the air as heat or sound, but there's always going to be a transfer of that momentum. So what we can influence, we can't influence how much momentum is transferred. That's going to happen. Law of conservation of momentum. Momentum cannot be lost or gained. It can only be transferred. But what we can do is we can change how long that collision lasts, and that's this concept of impulse. Impulse is determining how you experience the force of a crash. If the crash lasts for a longer period of time, say 5 milliseconds, versus 1 millisecond, that force that you experience gets spread out over that 5 milliseconds instead of all at once, bam, like a clap of the hands. Here's another example for momentum. In science, we say that momentum is conserved. That's basically a way of saying that momentum gets transferred from one place to another. And in this picture, we have a safety going in for a sack on a quarterback. How would we describe the transfer of momentum? Pause the video, think about how you would describe that, and then come on back. Okay, so how would we describe the momentum? Well, what's happening here is we have the momentum from the safety getting transferred to the quarterback. And that could cause, obviously, some problems a little later on down the road. We'll talk about that in a second. We can also think about it in terms of baseball. Okay, a baseball pitcher claims that he can throw the ball with as much momentum as a speeding bullet. Is that really possible? what would have to happen to his pitch? What would he have to do to his pitch to make it as hard to stop as a speeding bullet? You can pause the video and think about that. Okay, welcome back. We can actually calculate that. So let's calculate it. If we know the mass and velocity of the bullet, we can use that information to help us with calculating the momentum of the baseball. So let's do some quick calculations. Remember, momentum is the Greek letter rho equals mass times velocity, and we have both of those quantities right there. So we have that momentum is equal to 0.003 kilograms times 500 meters per second. Okay, let's do the calculation real quick. 0.003 times 500. We get 1.5 kilograms times a meter per second, which is the unit for momentum. Now we can use this number for the momentum of the baseball. So we have 1.5 kilograms times a meter per second. You know, there's something this picture is missing, and it's the magic circle. So I'm going to go ahead and draw the magic circle if I can draw one properly. Wow. Okay, I got this. I can do this. I got this, folks. Okay, so I'll draw the magic circle. Momentum is equal to mass times velocity. And so if we cover up what we're looking for, we're trying to find how fast the baseball would have to go to have the same momentum as the bullet. So I cover up the V, that's momentum divided by mass. The mass of the baseball is 0.145 kilograms. I will do the computation here, divided by 0.145, and we get 10.3 meters per second. Notice how kilograms cancel here, so we're left with meters per second. We know we've calculated it correctly. That's how fast a baseball has to be going in order to have the same momentum as a bullet. And I know you may be thinking to yourself, so what? Okay, I don't think in meters per second. Well, let's actually convert this into miles per hour, something that you can actually wrap your head around. Okay, there are 3,600 seconds in 1 hour. Seconds cancel. There are about 3.1 feet in every meter. Meters cancel. Now we're at feet per hour. We want miles per hour. There are 5,280 feet in 1 mile. Okay, so I'm going to take 10.3 times 3,600 times 3.1 divided by 5,280 equals 21.8 miles per hour. Hold on a second. Wait, that doesn't make sense. All you have to do is throw a baseball 22 miles per hour for it to have the same momentum as a bullet? A bullet can kill you. A baseball maybe just injures you unless it hits you in the head. So what's going on here? Well, there are other aspects of science that we could bring into this, and that is the concept of pressure. Pressure is how bullets and swords work. Pressure is equal to force divided by area. So when that bullet or baseball strikes you, the smaller the number for area, the bigger the number for pressure. And so swords work because the tip of the sword is pointy. It doesn't have a lot of area, making for a very big pressure when you stab it at someone. And a bullet is very, very tiny. It concentrates that force into a tiny little area for a greater pressure than what the baseball would do. Now, of course, a baseball can hurt you, okay, especially if it hits you in the head. But all you have to do is throw a baseball about 22 miles per hour in order for it to have the same momentum as the bullet. All right? Here's a review of Newton's laws of motion. First law, okay, back to the quarterback example. So before the hit, the quarterback was not moving at all. What had to happen to make him fall to the ground? In other words, is he an object at rest or is he an object in motion? And what's going to happen? Think about that for a second. Pause the video and then come back. Okay, so the quarterback, when he's hopping around looking for a receiver, he's basically not moving. Okay, he's an object at rest, and we know that objects at rest tend to stay at rest unless acted on by an outside force. Ho, there's the outside force right there. Okay, so the quarterback's going to stay at rest until that outside force acts on him. Now, notice where the force is being applied. The force is being applied to his torso, not his whole body. So The torso will start to move, but see his head snapping back? This is why you pay your left tackles, folks. Okay, left tackle protects the backside of the quarterback. If the force is being applied to his torso, the tendency of his head is to stay at rest. That's how neck injuries happen in football. Okay, what about Newton's second law? Same situation, Newton's second law. Why would it be harder for the younger brother to tackle this, or why would it be harder to tackle this quarterback compared to his younger brother? Okay, pause the video and think about that question for a second. Welcome back. Okay, so why is it harder to tackle the quarterback compared to his younger brother? Well, his younger brother is less massive. And as we know from Newton's second law, the less mass that you have, the easier it is to get an object moving. The more massive, the harder it is to get an object moving, and that is due to the grip between that object and the surface. The more grip it has because you are interlocking the jaggedy surfaces of the quarterback and the ground if he's more massive, versus if he's less massive, it's easy for you to move that quarterback. You don't have as much grip to contend with. What about Newton's third law of motion? So what are the action and reaction forces here? And what do we know about the strengths of those forces? Pause the video and see if you can maybe draw the arrows in your mind as to what the action force would be and what the reaction force would be. Okay, welcome back. I'm going to do my best to try to draw this because all I have on me right now is a pencil. The action force is the safety acting on the quarterback. I know that's really hard to see. Okay, we'll draw it there. So he's the action force. The reaction force is not the quarterback going to the ground. The reaction force is the quarterback pushing back on the defender. So action force, defender pushes. Reaction force, quarterback pushes back. And so that's step one. Step two. Step three is the QB goes to the ground. It's a big misconception people have, is that they sort of skip step two. They think that the reaction force is number three, the actual motion, but the reaction force is the quarterback pushing back. Okay, other things that you got to be aware of relating back to Newton's second law is the force of friction, sliding friction. What is an example when we do not want friction? Try to think of one of those examples. Pause the video. Okay, welcome back. You got an example? What is an example when we do want friction? Okay, well, we want friction when we're walking so we don't slip on an icy sidewalk, when we are driving in a car. You don't want your car slipping around because that can result in accidents where someone could get injured. So walking or driving in a car. Now, why would you rather slide down a metal slide than a slide made of sandpaper? Pause the video, think about it. Okay, well, the sandpaper is rough. That sandpaper has grip, and that grip resists motion. Friction is the resistance to motion, but it's also needed to get something moving in the first place. Last but certainly not least for our review, going all the way back to the start of the term, a couple weeks ago, we have some key differences between velocity and speed. What do they have in common? What do they have that's different? Pause the video and think about what's the same between velocity and speed and what's different between velocity and speed. Okay, welcome back. Same. Velocity and speed. Wow, okay, I can do this. I got this. Both measure how fast something is moving. And yes, we can calculate it. You know what this is. The magic circle! So, speed or velocity is equal to distance divided by time. They are both represent the same thing. They both are calculated in the same way, but there's a key difference between velocity and speed. We already talked about how speed is how fast, and velocity also includes how fast. But velocity includes something else, direction. And direction is important in physics, hugely important, because if you don't know what direction you're moving, you don't know how easy or hard it's going to be for you to avoid a collision. And so hopefully this helps you out. If you miss class on Friday or Monday so you can prepare for the quiz, and I will catch you later. Peace out.